Hello guys, welcome back to hands-on for lecture 7. In this hands-on, we are going to do some regression analysis using Python. So let me start my Jupyter notebook. Okay. So in this, we are going to use the mtcurs dataset. And here is the bunch of packages that I have called. Here I have bunch of packages: NumPy, Pandas, Matplot library, SciPy. From sklearn we imported linear models. From sklearn's matrix we calculated R2 score. Then some other models from statsmodels, stats API. So all these things we have computed. Let me run it. It ran. It has no problem. So next is read the mtcurs dataset and trade, and it has 32 rows, 11 column as expected. And head. So it has first column is miles per gallon. Second column is cylinder, third column is displacement, fourth column is horsepower, rear axle ratio, weight, Q-sec, V shape or not, automatic or manual, how many gears it has, and carburetor. So the first we are going to plot weight versus miles per gallon, and as expected on the x-axis we put a weight, and on the y-axis we put gallon, miles per gallon, and there is a negative relationship. What we are seeing is as the weight of the car increases, efficiency of the car drops. So first we are going to fit a linear model with weight using a sklearn. So we are going to fit miles per gallon as a function of a plus b times weight plus error. So x is in the weight and y as the miles per gallon. And from the linear model, we are calling the linear regression module, defining it as a LM. And then we are going to fit LM fit, and x we have to give this x, and for y we have to give this y, and that will be fitted as a first model. Okay, so it is done, and from the fit m1, here it is, we are extracting the intercept and calling it intercept and the coefficient beta, and we print it as b equal to a equal to and b equal to. So we got a equal to 37.28 and b equal to negative 5.344. And we are going to calculate y hat equal to intercept plus, in dot operation we are going to do x into beta. So but it's a dot operation. From NumPy we are going to call the dot operation. So we ran it. We took a equal to 37.285 and b equal to negative 5.344 from here, and then we are going to draw a straight line, AB line sometimes called, through the plots. So this we have written this small piece of function which, if you give the slope value and the intercept value, it will plot the line from slope and intercept over the scatter plot. So we run this. So over the scatter plot we draw a straight line, and this is the best fitted OLS line. Now we are fitting a model evaluation. Now we are fitting a R square. R square is 0.753, and then from the we have y and y hat. We plot y and y hat. Y is the miles per original miles per gallon, and y hat is the predicted miles per gallon or estimated miles per gallon. So we can see that they are positively correlated. That means the cars which has lower efficiency, it is predicted as lower, but definitely there are some variability. More tight it will be, better the model prediction is, we can say. So now fit linear model using weight using stat model. So that was, we fit this model using, so when we fit this model in the above, yeah, here this was done using sklearn. Now we are going to fit the same model using stat models. So sm.ols, if we run that, it gives printout more like a, like a R kind of printout. Now along with weight we want to put the horsepower. So in the X we put, along with weight we put the horsepower, and we fit the model. Now we are preparing a new data with a new prototype car with weight equal to 3 and horsepower equal to 120. So in that we run. So we got the alpha and beta. Now beta will have two coefficients, so that's why it is 2 cross 1. Now predicted values will be for that, for a new prototype car which has 3 weights and weight equal to 3 units and horsepower equal to 120 units, we'll have a miles per gallon 1.78. So we can calculate the total sum of square. First you calculate y hat, then y minus y hat, and that if you square it, that will give you error sum of squares. Okay, and then if you just take sum, that will give you the total sum of squares. And then if you just calculate, divide that by n minus p minus 1, that will give you the mean sum of square. So the residual standard error is just take the square root of mean sum of square, that will give you the residual standard error. Okay, now so the residual standard error for this model is 2.59. Now miles per gallon, that means follow normal beta naught plus beta 1 times weight plus beta 2 times horsepower, comma sigma square. So residual standard error is an unbiased estimator of the sigma square. So we can calculate the lower bound as predicted value minus 1.96 times residual standard error, and upper bound would be predicted value plus 1.96 times residual standard error. And we print the lower bound and the upper bound. So the lower bound will be 16.69 and upper bound will be 26.86. So for next we fit R square is 82.67%. So along with weight, when we put horsepower, the R square jumped to 82.6% and it becomes slightly tighter. Now let's explore the relationship between horsepower and miles per gallon. So what we are seeing, the relationship is, maybe there is a quadratic relationship. So we have to do some feature engineering. So we add a new column by simply taking the square of the column, and then x head is you have weight, horsepower and horsepower square. Now we can fit the third model by just providing the proper x and y and use the predict to get the predicted values. So the model evaluation, when we do the model evaluation, what we find that the whole and the R square has gone up to 85.8%, and it is becoming more tighter now. And if we fit the OLS way, R square is slightly different, 83%. We are saying adjusted R square is 82%. So this is the sklearn. Remember that sklearn's calculation is 85.8%, whereas statsmodels is giving us a slightly different 83%. Okay, and this is our data set with a new data set, and then when we fit the OLS in this way, okay, interesting, when we fit the OLS in this way, what we have seen that R square is now 85.8%. so maybe this is the right way of fitting the model. Okay, so okay, previously it was fitting the the old way. Okay, and now we have to do some model as checking the model assumptions. If you want to check the model assumptions, what you do, first you define the residuals and plot the residuals against the predicted value. So we see that there is not much going on, so we can do a Bruch-Pagan test for homogeneity, and the p-value is quite high. So from the Bruch-Pagan test we cannot reject homoscedasticity. We can say safely that it is homoscedastic behavior. It has a homoscedastic behavior. The histogram is sparse. We can run a Kolmogorov-Smirnov test. The p-value is marginally small. So in the previous also we saw that Kolmogorov-Smirnov test was marginally smaller, giving us a indication that there could be questionable, the normality could be questionable, though other tests could be fine. So with this I'll stop.